Assalamu alaikum. Today we want to talk about chapter 8, part 3. You remember until now we talked about ionic bonding and covalent bonding, and we saw how in ionic bonding one electron is lost from a metal to a non-metal. And in covalent bonding, there is no loss of electrons rather than sharing of electrons between two atoms. Now, how to differentiate between ionic and covalent bonding? Now, the simplest approach is to assume that the interaction between a metal and a non-metal is ionic, example like in NaCl we talked about, and that between two non-metals is covalent, example between H and Cl. Now, a more sophisticated approach is to use the difference in electronegativity as the main criterion for determining whether ionic or covalent bonding will be dominant. Now, this approach correctly predicts the bonding in SnCl4 to be polar covalent based on an electronegativity difference of 1.2, and at the same time correctly predicts the bonding in NaCl to be predominantly ionic based on an electronegativity difference of 2.1. Therefore, it is not surprising to learn that, for example, manganese 2 oxide MnO is a green solid that melts at 1842 degrees centigrade and has the same crystal structure as NaCl. However, the bonding between manganese and oxygen is not always ionic. Manganese 7 oxide Mn2O7 is a green liquid that freezes at 5.9 degrees centigrade, which indicates that covalent rather than ionic bonding dominates. Now, the change in the oxidation state of manganese is responsible for the change in bonding. So, in general, as the oxidation state of a metal increases, so does the degree of covalent bonding. Now, when the oxidation state of a metal is highly positive, roughly speaking, +4 or larger, we should expect significant valency in the bonds it forms with non-metals. Thus, with metals in high oxidation states, we find molecular substances such as Mn2O7 or polyatomic ions such as MnO4-1 and CrO4-2 rather than ionic compounds. Lewis structures. Now, Lewis structures can help us understand the bonding in many compounds and are frequently used when discussing the properties of molecules. If we have two atoms of hydrogen, they share the two electrons between them. And for Cl, 7 electrons, each one share 1, so each one has an octet around it. So Lewis structures are representation of molecules showing all electrons bonding and non-bonding. So for this reason, drawing Lewis structures is an important skill that you should practice. And to do so, you should follow the following procedure. First of all, sum the valence electrons from all atoms. For example, we want to draw Lewis structure for PCl3, P in group 5, so 5 valence, Cl in group 7, 7 valence times 3. The total is 26. So, now, if it is an anion, add 1 electron for each negative charge. If it is a cation, subtract 1 electron for each positive charge. Then, the central atom is the least electronegative element that isn't hydrogen, of course. Now connect the outer atoms to it by single electron by a single bond, as you can see here, by single bonds. Keep track of the electrons. Now, total 26 minus 2 plus 2 plus 2, 6 bonding. 20 electrons remain. 20 electrons remain. Now, complete the octets around the atoms bonded to the central atom, the Cl's. We complete the octet here. Remember, however, that the hydrogen atom has only a single pair of electrons around it. So now, so remember, we have 20. Now we have 8 times 3. Here we have 6 times 3, 18. So 20 minus 18, 2 electrons remain. Now place any leftover electrons on the central atom here, even if doing so results in more than an octet of electrons around the atom. So you see here, 2 minus 2 is 0. Now, if there aren't enough electrons to give the central atom an octet, try multiple bonds. Like in this example, even if you run out of electrons before the central atom has an octet, then form multiple bonds until it does. So here, now when we sum the electrons here, 1 plus 4, 5 plus 5, 10, and here we have 10, but carbon should obey the octet rule, has only 4, so we put one double bond. Still does not obey the octet, we put another double bond. Now we have triple bond here between carbon and nitrogen. Remember, between carbon and hydrogen, only a single bond, one single bond exists. So always, if you run out of electrons before the central atom like this has an octet, then form multiple bonds until the central atom obeys the octet rule. Use one or more of the unshared pairs of electrons on the atoms bonded to the central atom to form a double or triple bond. So here we use the first pair, we put the first, then we used the second pair, we put, so here nitrogen has only one lone pair remains. Now we come to the concept of formal charge and alternative Lewis structures. Now, when we draw a Lewis structure, we are describing how the electrons are distributed in a molecule or polyatomic ions. In some instances, we can draw more than one Lewis structure and have all of them obey the octet rule. Now, all these structures can be thought of as contributing to the actual arrangement of the electrons in the molecule, but not all of them will contribute to the same extent. How do we decide which of several Lewis structure is the most important? As you can see, one approach is to do some bookkeeping of the valence electrons to determine the formal charge of each atom in each Lewis structure. So the so-called the formal charge of any atom in a molecule is the charge the atom would have if all the atoms in the molecule had the same electronegativity. Now, so to assign formal charges. For each atom, count the electrons in lone pairs and half the electrons it shares with other atoms. So here, for example, in CO2, this atom, how many valence electrons? Group 6, 6 electrons. Now, how many electrons are assigned to this atom by this Lewis structure? It is the sum of non-bonding and half bonding. So 2 plus 2, 4. and 1/2 for bonding, so total 6. For carbon 4 and half bonding, half the 8 is 4. And this atom like this atom. And you subtract, so formal charge is 0, 0, 0. So the difference is the formal charge. So you have here, now all unshared electrons are assigned to the atom on which they are formed, like these. For any bond, single, double, or triple, half of the bonding electrons are assigned to each atom in the bond. Now, if we calculate formal charge for this Lewis structure, we see here we have a -1 on this oxygen, +1 on this oxygen, 0 on this carbon. Now, so let's look at this sample exercise 8.9, Lewis structures and formal charges. Now, there are 3 possible Lewis structures for thiocyanate ion and Cs-. You can see this. Determine the formal charges of the atoms in each structure, and in B, which Lewis structure is the preferred one. So let's determine the formal charge. Nitrogen, the valence electrons 5 in group 5, and now the number of electrons assigned to this nitrogen by this Lewis structure, 2 plus 2 plus 2, 6, and then half the 2 here, half the bonding, 7. 5 minus 7 minus 2. For carbon, 4 minus 4, 0. For sulfur, group 6, 6 valence, and here the electron assigned here, all the lone pairs, 2, and half bonding. Half the 6, 3 plus 2, 5. So 6 minus 5, it is +1. And in the same way, you calculate for the others. As they must, the formal charges in all 3 structures sum to -1, the overall charge of the ion, -1, -1, and here -2 plus 1, -1. Now, determine which Lewis structure is the preferred one. Here, you see. Now, we will use the guidelines for the best Lewis structure to determine which of the 3 structures is likely the most correct. Now, first of all, the dominant Lewis structure is generally the one in which the atoms bear formal charges closest to 0. Second, a Lewis structure in which any negative charge resides on the more electronegative atom is generally more dominant than one that has negative charges on the less electronegative atom. So here, -1 on nitrogen, -1 on sulfur. Now, you see, nitrogen is more electronegative than sulfur, than carbon or sulfur. Therefore, we expect that any negative charge will reside on the nitrogen atom. So this is the preferred Lewis structure. Further, we usually choose the Lewis structure that produces the formal charges of the smallest magnitude. For these 2 reasons, the middle structure is the preferred Lewis structure of the NCS- ion. And here you can do this practice exercise by yourself. Again, these are the formal charges. Which one is the preferred one? طبعا لاحظوا هنا negative charge is on oxygen or on nitrogen. طبعا oxygen is more electronegative than nitrogen. So the most electron of the 3 is the preferred Lewis structure. So structure 3 is the preferred structure. Structure 3 is the preferred structure. So again, the best Lewis structure is the one with the fewest charges. So you omit this. Now you compare these 2. Then puts a negative charge on the most electronegative atom, nitrogen or oxygen. Of course, oxygen is more electronegative, so this is the preferred Lewis structure. Now we come to talk about resonance structure. Now, we sometimes encounter molecules and ions in which the experimentally determined arrangement of atoms is not adequately described by a single dominant Lewis structure. Consider, for example, ozone, O3, ozone. This is the Lewis structure we would draw for ozone, O3. Ozone is a bent molecule with two equal oxygen-oxygen bond lengths. Now, because each oxygen atom contributes 6 valence electrons, the ozone molecule has 18. 6 times 3, 18 valence electrons. So this means that the Lewis structure must have one oxygen-oxygen single bond and one oxygen-oxygen double bond to attain an octet about each atom. Like this. However, this single structure cannot by itself be dominant because it requires that one OO bond be different from the other. And if this is the only form, this is a single bond, this is a double bond, but this is not true. In the actual molecule, these two bonds are with the same length, which means they are equal. So in drawing the Lewis structure, however, we could just as easily have put the OO bond on the left. So then again, this is at odds with the true observed structure of ozone, in which both oxygen-oxygen bonds are the same length. Both outer oxygens have a charge of -half, both of them, and the angle, as you can see, is 117 degrees. So what is the solution? So when Lewis structure cannot accurately depict a molecule like ozone, this or this, no. So what we do, we use multiple structure, resonance structure to describe the molecule. Just as here, green is a synthesis of blue and yellow. Now ozone here is a synthesis of these two structures, where the double bond one time here and the second time here. So then the actual Lewis structure is a resonance hybrid of the two I showed you. Now, in truth, the electrons that form the second CO bond, if we look here at this this structure, and we draw two resonance structure for it. Now, the electrons that form the second CO bond in the double bonds below do not always sit because that's carbon and that oxygen, but rather can move among the two oxygens and the carbon. Then one time the double bond here, and the second time the double bond here. So these two are called now resonance structure. As the actual arrangement of the electrons in molecules such as O3 must be considered as a blend of two Lewis structures, here again the actual structure of this ion HCO2- is a blend of these two structures. Now, whenever the electrons are between two atoms like this, we call them they are localized. But if there is a double bond, and this double bond can move here, as you can see, we call them delocalized electrons. So here, delocalized electron versus this one is localized between hydrogen and carbon. And again, you can we can see this sample exercise again for the sulfur atom has 6 valence electrons. Now the question, what is predicted to have the shorter oxygen bonds, SO3 or SO3 minus 2? So we draw structures for SO3 first and then for SO3. Now in this we have 3 resonance structures. They are all equivalent. So as the actual structure is equal blend of these, so each SO here bond distance should be about 1/3 of the way between that of a single and that of a double. That is, they should be shorter than a single bond, but not as short as double bonds. However, in the SO3 minus 2 ion has 26 electrons, which leads to a Lewis structure in which all the SO bonds are single bonds. So this is single, this is a pure single, so this is longer than any of these 3. This is shorter. So there are no other reasonable Lewis structure for this ion. It can be described quite well by a single Lewis structure rather than by multiple. Our analysis of the Lewis structure leads us to conclude that SO3 should have the shorter SO3 SO bonds, and that SO3 minus 2 the longer ones. This conclusion is correct because the experimentally measured SO bond lengths are 1.42 here angstrom and 1.51 angstrom in SO3 minus 2. This is the example that I explained. Okay, now the last topic in this chapter is resonance in benzene. Resonance is an important concept in describing the bonding in organic molecules, mainly aromatic organic compounds. And a category that includes the hydrocarbon benzene C6H6 has 2 resonance structures, as you can see here. We can write 2 resonance structure for benzene. Note that the double bonds are in different places in the 2 structures. لاحظوا هون double هون single وهكذا. So they are different. Now each of these resonance structures shows 3 carbon-carbon single bonds and 3 carbon-carbon double bonds. However, experimental data show that all 6 carbon-carbon bonds are of equal bonds, 1.40 angstrom, intermediate between the typical bond lengths for a carbon-carbon single bond, 1.54 angstrom, and a carbon-carbon double bond, 1.34 angstrom. Now, each of the carbon-carbon bonds in benzene can be thought of as a blend of a single bond and a double bond. So, as you can see, it is commonly depicted as a hexagon with a circle inside to signify the delocalized electrons in the ring. And the shorthand notation reminds us that benzene is a blend of 2 resonance structures. It emphasizes that the carbon-carbon double bonds cannot be assigned to specific edges of the hexagon. So chemists use both representation interchangeably. End of part 3 in this chapter 8. Thank you.